Okay, welcome back everyone to week two's problem solving session. So we will begin from where we had left in week one. So in week one, just to give a quick recap, what we looked into is the basics of fluid kinematics, involving some things known as material derivatives. Then basically, using, so we also learned how to use the Reynolds transport theorem, and then using Reynolds transport theorem and conserving mass to eventually calculate what will be the rate of change of head of an inflowing tank. This is something that we have done in the last class. And uh, and yeah, so as I said, we looked into evaluating material derivative. For instance, when given the velocity field, we looked into how to evaluate the acceleration. And then given that we have a scalar field, for instance, like the density field inside uh, maybe, so for instance, we had the density field and a velocity field inside a diffuser, and then we were asked to basically evaluate what is the rate of change of density at a given prescribed length. And then we also looked into how to evaluate certain quantities, for instance, like the angular velocity and the vorticity given a flow field that we have. Okay, so we'll do a quick problem in this, in addition to this. And I believe this problem is very similar to the one that is there in the assignment of week one. And I expect you have attempted to solve this problem in the previous week's assignment, which I believe you have already submitted. Nevertheless, we will try to see how to solve this problem, because I feel this is a very important problem in association with Reynolds transport theorem. Uh, and how do so this is kind of a similar problem that we solved it in the previous week, where we actually calculated the rate of change of head because we had two inflows that were there inside the control volume. This problem is little bit different, although it's very similar. The difference lies now in the fact that we have an inflow velocity of water, which is given as a u infinity, and this is assumed to be constant, meaning that in this cross section the profile of the inflowing water is assumed to be uniform. But the only difference that lies with this problem to the earlier problem that we have solved in the previous week is that now there is an outflow of water which is taking place, and as a result of which the head of the tank is maintained to be constant. So the earlier problem which we solved had actually varying water head, or the height of the control volume was changing with time, and that was the prime objective that we were asked to evaluate, that what is the rate of change of h with respect to t, or how does h vary as a function of time. But here it's the other way around, that we are saying that, okay, since I have a net inflow and a net outflow that is going inside the tank, I am saying that, or in fact the question says that the head is now kept constant. And then what we need to do is, and of course, I believe you understand that in order to keep this head as a constant, you also need an equivalent outflow, right? And that's the only way you can keep the head constant. And this outflow is taking place in this direction, as you can see in the figure. So given this scenario, what they have asked us now is to evaluate a relationship between the incoming fluid velocity, which is uniform, given by its magnitude u infinity, with u naught, where u naught is actually the, you can consider it as the maximum of the changing velocity profile that we encounter in the outflow pipe. Now here it is where, there is a little bit of difference that we also saw with the sum that we solved it in the previous week. Because the water profile that is flowing outside of that, I mean, that is going outside of the control volume, this is now not assumed to be uniform. And this is more of a practical scenario that they are saying us, where the the velocity profile, which is given by this, as you can see, is essentially varying with the local y coordinate of the pipe. Meaning that if I draw the velocity profile here in the pipe cross section, it will typically see when y1, so if I choose my axis to be in the middle of the pipe, then you can see that when at these points, that is at y1 equal to plus and minus of h. So when y1 is equal to plus and minus of h, if you substitute here, you will see that u is basically equal to 0, which means that instead of having a constant velocity, you actually have zero velocity field at the point where the fluids meet, where the fluid meets the wall. And then you have a parabolic velocity profile of this form, maybe. Okay, the variation of which is given by this velocity profile. Okay, so I believe you understand now the difference, that instead of having a constant velocity profile in the inflow or the ones that we solved it in the previous week, okay, we now have a velocity profile that is actually varying along the local y coordinate of the pipe. And this is something that we need to account for when we are using the Reynolds transport theorem. Okay, then as I said, the relation, I mean, the objective is simple. We just need to find the relationship between u naught and u infinity. And for which I'm guessing that you guys must have thought of the answer. I mean, thought of the solution procedure is that we'll apply the Reynolds transport theorem. Uh, and obviously by conserving mass. Okay, so let's do this. So all right. What we'll do is I'll not go into the much detailed steps because we have already seen this kind of problem in the previous week. So we'll say that just applying RTT of course stands for the Reynolds transport theorem for mass conservation. Okay, and if we apply RTT, we will eventually see that. So the left hand side we know is 0 when we are conserving mass, because this is typically so the left hand side signifies the rate of change of mass inside a controlled mass system, which is 0, that we all know. The left hand side, or sorry, the right hand side is the first term, which speaks about the rate of change of the property inside the control volume, which is del T of integral over the entire control volume times rho dV, where I must now draw my control volume. So I'll choose my control volume as this, as the one of the water that is encompassing the water level inside the tank. This is my control volume. So this typically is my control volume, where now I have two control surfaces. One is this surface, which we'll call it as 1, through which we have water coming inside the tank, and the other is 2, through which we have water that is going outside the tank. Okay, I believe this is clear. All right, then the efflux terms then come out to be integral closed surface integral over the control surface rho, the velocity dot n hat, where n hat we all saw this is the unit normal that is outward towards the control surface, times the elemental area dA. All right, so now what we can see is, again we'll assume that my density is constant, so there is no change in density. You can equivalently say that it's an incompressible fluid, which then means that I can then simplify this to integral over the control volume dV. Okay, and there is a del T over here. Plus, let's keep this as integral over the control surface V dot n hat dA. Now, when we evaluate these terms, integral over the differential volume times the, so if we pick a differential volume inside the control volume and then integrate it over the control volume, we will eventually see that this basically goes out to be equal to the area of the tank times the water head, which is H, which is typically this head that we are considering. Okay, so if we evaluate then this, if we then evaluate this, this will simply be equal to del, so AT is constant, or maybe you can write it as del T of AT times H, okay, plus the net efflux, which is for time being, we'll just keep it as like this. Now, the difference that we will encounter with this problem with respect to the earlier problem that we solved it in week 1, or I mean, in the previous week, is that we, in that problem, since there were two inflows inside the tank, the water level was continuously rising with time. Okay, but here, since we know that the water that is coming in and is, so the inflow is equal to the outflow, which results in the tank maintaining a constant water head, will be used in the fact that this quantity, this AT times H, AT is anyway constant because this is the cross-sectional area of the tank, but this H is now no longer a function of time. Okay, and the physical significance is that since there is a net inflow, so the net, so the fluid that is coming in is equal to the net flow that is going out. So the head of water is constant, which means that you know, or basically it's like the water head is constant, which then means that this term dH by dt will simply, go out to be equal to 0. Okay, which was not 0 in the earlier case where we had, two inflows, and as a result of which the level of water was rising. Okay, so then this term will basically, go to oblivion. This will basically go to 0, which means we just end up having closed surface integral of v dot n hat equal to 0. Okay, that is something that we need to evaluate in order to get a relationship between u infinity and e naught and u naught. Okay, then let's evaluate this quantity at the two control surfaces. So we have one surface, which is this, where, there's a uniform, flow of water that is coming inside the control surface. So for the inlet, let's see. So I'll draw the inlet maybe separately here. So we have this inlet of this form, and this is typically what the control surface would look like. Okay, so what we can see is that if I pick the unit normal to the control surface, the unit normal would be, I hope you can imagine that the unit normal of this control surface would be along this. So this is typically your n hat. Okay, while the fluid velocity is in this direction, which is u naught. Okay, so at control surface 1, this integral would just boil down to be minus of, because of the fact that v dot n hat will have a negative sign, and the idea is something that we have discussed it in the previous class. So this is just going to be u naught times, so what this is going to be? So this is going to be u naught times this height. Okay, so this height is given, uh, I mean the thickness of the pipe, this is given to be equal to h times the width, which is actually in a direction which is perpendicular to the plane that I'm writing. So this is going to be u naught times h times b, where b is the width of the pipe typically. So you can think of it like a parabolic, so it's like a uniform flow taking place between two channels. This is something that you can think of this example as like, I mean, think of this inlet 1 as this. Okay. All right. So this is something that happens at inlet 1. And then let's try to see for inlet 2. So at inlet 2, what do we have? So the inlet 2 is something like this, okay, where we have, some variation in the velocity profile. That is something that we discussed. So this variation in the profile is that your u as a function of y1, where your y1 is the local y coordinate, is u naught times of 1 minus of y1 squared by h squared. Okay, is your velocity profile. That's the velocity profile that is given, where again the h is going to be this this well, h is going to be this distance. And then if we now, so but now there's an important thing. Okay, so now if we look into, so for instance we have, you know actually I should draw the control surface. So this is what the control surface would actually look like. Okay, this is typically what it would look like. It is not actually this one, but it is actually this, because then only the n hat, the normal, would be along this direction. So then if I draw the control surface for this, if I now draw the control surface for this, you can see that the unit normal in this direction is, so maybe this is something that we'll call it. So this unit normal, I'll call it as n1 hat, and then this unit normal, I'll call it as n2 hat. Okay, or maybe so this unit normal is n2 hat, and you can see that now the direction of the velocity is in the same direction as the direction of the unit normal, which means the dot product now will be not -1, but it will be +1, because again, I stated that whenever there is an outflow taking place, the directions of the unit normal and the direction of the velocity vector is in the same direction, which means that the dot product would give us a positive signs, opposite to the case that we considered in the inflow case, in the inflow direction. Okay, so then this dot product would simply give you plus, but here is something that you need to understand. So the direction is taken care of, but you need to understand that when you move along your, y direction, or y1 direction to be precise, you are actually seeing a change in the velocity profile. Okay, so your velocity profile, which has a magnitude of u naught at y equal to 0, is changing from u naught to 0 when we move along this y direction, which means now you cannot use this as a uniform velocity profile, and rather what you need to do is you need to pick a differential volume inside this pipe and then find the differential flow rate and then integrate the differential flow rate throughout the along the along the cross section of the pipe. Okay, which means the net or the total outflow would basically be integral from minus h uh, to, I don't know. This is okay. So this is your axis. Let me draw the axis first. Okay, so let us draw the axis. So this is maybe your x direction, which is x1, and this is your y1, and this entire distance is considered to be h, which means that your integral would now be from minus h by 2 to plus h by 2 times the differential flow rate, which is going to be u naught of 1 minus y1 squared by h squared times the elemental area, which is going to be b times dy. I hope you can understand what I have written in this term. Okay, so this is very simple. That is typically because since there is a variation in the velocity profile, what you need to do is you need to calculate the differential volume flow rate and then integrate the differential volume flow rate throughout the cross section from minus h to plus h to get the entire flow rate basically. And then this is equal to 0 because we know that this 0 basically is coming from here. And then it's just simple. What you need to do is maybe I can take the u naught hb to the other side. Okay, and then this would be integral from minus h by 2 to h by 2 u naught of 1 minus y1 squared by h squared times b dy. Okay, and then it's just very simple. If you do this integration, and I believe you guys are at least expert now in doing integrations. So if you just do this integration, you will see that you will simply get a relationship of the form u naught equal to 12 by 11 q infinity. Okay, this is something that you will get. Okay, when you just take this integration, see this h this b will basically cancel from each other because your b is just the width. So this b and this b will cancel, and if you take and if you do this integration, you will actually get a term containing u naught times 11 by 12 times h, and then this h and this h will cancel, and then you will just end up getting u naught equal to 12 by 11 times u infinity. It's just the integration that you need to do, and I believe that you guys are well equipped with doing these sort of simple integrations. All right. So the idea of this exercise, and this is a very similar problem that is there in your assignment, and I believe you guys have done this problem, is to show you that is to show you two things. First of all, the direction of the unit normal and the direction of the velocity vector when there is an inflow and an outflow. We saw that when there is an inflow, the unit normal is in the opposite direction to the velocity vector, because of which we encounter this negative sign. And if there is an outflow, the unit normal and the velocity vector is in the same direction, as you can see, and because of which the dot product end up giving us 1 in that in this scenario. And then also to show that when you have a varying velocity profile, you just simply can't take the average as we have, or you just can't simply write the velocity profile as u naught, typically because your velocity profile is itself varying with the local y coordinate. Okay, see, if this term had been equal to 0, you will simply get this term, which is u naught h by b. Okay, you can do this quick check at your end, and then this is typically, so then you will get a uniform inflow and a uniform outflow. That's all that we'll get, and this will trivially be coming out to be equal to 0. I mean, that's obvious, right? The net inflow is a uniform velocity profile, and the net outflow is also an uniform velocity profile. Okay. uh, but since we are, in this case, we are having a velocity profile which is varying along this space. So we, instead of just writing u naught hb, you actually need to integrate it along the direction in which you see a change in the variation in the velocity profile. Okay, so these kind of things we will so these variation and these kind of integrations we will encounter frequently, and I hope you are getting this concept through this problem. Okay, with this, let's get started with the contents of week 2. And I hope you have gone through the lecture series of this week. Second. The recording is going on. The recording is okay. So yeah, so I was telling that I believe we have gone through the lecture series videos of this week, where you saw certain simple solutions to the Navier-Stokes equation. So now we'll actually encounter viscous fluid flows actually, where we will primarily now dive into the actual applications of viscous fluid flow. Week one is just the recapitulation. That is something that you can say. But now we will actually learn true concepts that involve, you know, using that involve viscous fluid flows. Okay. And the first, and yet I would say a very simple case, is something that you have already seen through the lecture series videos of this week, is known as the unidirectional rectilinear flows, where you saw that your velocity profile, for instance, like the x directional velocity profile, if you have a flow known as the Couette flow, where the upper plate was moving with some velocity and the lower plate was stationary, which actuates the flow in between these two plates, and you saw that the flow was in the x direction with its variation in the y direction. So your u, which is the x component of velocity, is primarily varying along y. This is something that you saw when considering examples like the Couette flow or plane Coisebel flow or plane or simple plane or like planar parabolic flows and things like that. Okay. So that is something that you saw. You use something known as the Navier-Stokes equation, which again you can derive, and I believe you have done this using the Reynolds transport theorem, when you use the property to be momentum and your intensive property just becomes equal to the velocity. So that is something that we'll not do in the discussion hours, because that is beyond the scope of this discussion hour, is to derive the Navier-Stokes equation. I believe this has already been done in the theory classes, but the essence and the idea is that you write the you write the Reynolds transport theorem, choose your extensive property to be momentum, and then your intensive property becomes equal to velocity. Simplify, the so you will something. So what you will actually get is something known as the Cauchy momentum equation, and then if you use the stress strain relation, that your stress is equal to 2 times of strain, you will typically get the Navier-Stokes relation basically, or I mean the Navier-Stokes equation. Okay. Again, I say we'll not go into the derivation, but what we will do is we will start off by doing by giving a quick recap of the Navier-Stokes equation and how it looks like, and then after that we will use the Navier-Stokes equation into solving problems which involve calculating the velocity profile of flows like plane Couette flow and plane Coisebel flow. Okay, so let's get started. Uh, Okay, so what we saw is like using, as I said, using the Reynolds transport theorem for momentum. What you saw is the ultimate equation that we got is known as the much celebrated Navier-Stokes equation. I'll call it as NS throughout this course. And this Navier-Stokes equation, when written in vector form, took the following form. Okay, it is rho times the material derivative of velocity, which is capital dv dt, and then this is equal to minus gradient of the pressure times viscosity times del square of velocity times rho times the body force. Okay, so this is typically, as you guys must have derived this already, uh, this is typically the Navier-Stokes equation, but you have written this for an incompressible fluid. Okay. And since you have written this for an incompressible fluid, you also have the continuity equation, which takes the following form. Divergence of velocity is equal to 0. Okay. So these two equations is what will mostly, so, throughout this course, you will see that we will find strategies of actually solving these two equations. That's all is what actually the crux of this viscous fluid flow course actually is. Okay. So we will just find strategies of solving the Navier-Stokes equation. Of course, the scenarios will be different. So the scenarios will not be much simple or simpler as the ones that we will see today or in the next week. But as I said, the essence will be is to find strategies for solving this Navier-Stokes equation, or in other words, for finding the velocity field using the Navier-Stokes equation. Okay. So there are certain terms that you need to look that you need to be familiar with. For instance, this term that is rho times dv dt. This is associated with force due to inertia. Okay, and this gradient of P, maybe you can include the minus or not, that is up to you, but this gradient of P is the force due to pressure. And this mu times del square V is the viscous force. And this rho times V is the body force. But remember, when I say force, this is actually force per unit volume. Okay, so if you actually calculate the unit in this equation, for instance, the unit of this body force is Newton per meter cube. Okay, so if you multiply this body force with the volume, you basically get Newton, which is actually force. So actually, the quantities in the Navier-Stokes equations are not force, but it is kind of like force per unit volume. That's what we are actually interested in calculating. Okay. And of course, this is the continuity equation. We all know, we have been seeing this, so you don't need any, additional explanation to this. Okay, all right. So this is something that that we will see, and we will. So now the idea is, so I hope you can understand that from this equation, the unknown that we are actually trying to solve for is the velocity field. So this is the prime unknown. But remember, there is also one more unknown, which is there, and that is not known, which is actually pressure. Okay, see, pressure is also unknown to us, right? In general, at least until and unless we are given that there is an applied pressure gradient. Okay, pressure itself is not known to us. For example, there is a, so you can think of it like, for example, if there is a metal ball which is moving, or you can consider it like any spherical object which is moving through a fluid. Okay, due to its own intrinsic velocity. So you can think of it like an organism. Okay, an organism that is moving through a stationary fluid, and since that organism has life, it also has its own velocity, which we call it as the intrinsic velocity of an object in terms of fluid dynamics. Now, if that is the case, you don't know what is the velocity field that is being generated, or what is the velocity field that this organism imparts to the surrounding fluid. Okay, and the associated pressure field. For instance, what I'm saying is, let's say I have a microorganisms of this form. It So basically, how these microorganisms move is, they have something known as tentacles. And what they do is, they you can think of it like a so this blue object is kind of a microorganism, and it is actually moving in some direction, uh, which we'll call it as up, which is the linear velocity of this microorganism. For instance, we'll not consider the angular velocity now. Let's just consider that it just possesses linear velocity, and it is moving through, let's say, a stationary fluid, something of this sort. Okay, so this is the actual scenario that is happening. Okay, now typically how these microorganisms move is, they actually beat their tentacles in the fluid. And typically what actually happens is the Newton's third law. So if you exert force on the fluid will itself exert force on the organism, and that is how this organism kind of move forward in space, and then they generate some kind of a trajectory as they move forward, basically. Okay, in fact, this trajectory is kind of like tangential to this velocity. This is something that you can see. But anyways, this is actually how a it's not just a microorganism, but like, you can extend this to any organisms, in fact, beyond in any length scale. There is no limitation to that. But for instance, I'm just saying, it's like, think of it like a small insect that is moving through a fluid. Okay, and then, as I said, the motion of the insect, what it will do is, it will impart certain disturbances in the flow field. So as it moves in this trajectory, the flow field will also get disturbed. Okay, the flow field around this will basically get disturbed. But I know that since the organism is small enough, the flow field which is very far from the organism, they will remain stationary. Then the objective is to calculate what is the disturbance flow field. Okay, and also we don't know what is pressure, right? What is the disturbance pressure that basically gets imparted when the organism moves in this fluid, basically. So these two, the velocity field and the pressure, these are the unknowns here. Okay, and this we will get when we solve the Navier-Stokes equation and the continuity equation. which is precisely these two equations that you do that we have. So in principle, I hope you realize that in a three-dimensional space, which we are actually in now, because we as mechanical engineers, we are just interested in spaces that in dimensions that actually exist. For instance, like uh if this microorganism move in space, we are just interested in the x, y, and z dimension. That's it. So the unknowns that we will actually try to solve for while we are trying to calculate the velocity, field, and the pressure is going to be the x direction velocity, the y direction velocity, and the z direction velocity, and also pressure. Okay. So these are the components of the velocity field, plus we are solving for pressure. So in principle, we actually have at most four unknowns in a real life 3D problems. And see, we also have four equations, because see, this is a vector equation, right? This equation is a vector equation. You can extract three equations from this vector equation. For example, if you write your velocity as u times ex, that is something that we have done in the last class, v times uy, or w times ez, then you basically get three components of this, what we call as the Navier-Stokes equation. Okay, so these three components of the Navier-Stokes equation plus the continuity equations, which when you write it for a three-dimensional space, just simplifies to del u del x plus del v del y plus del w del z equal to 0. That is typically when you expand this gradient, this divergence operator, you will anyway get this form. Okay, so in principle, as I said, three component wise Navier-Stokes equation and the continuity equation is sufficient for giving you the four unknowns, which is the x, y, and z uh, components of the velocity field and the pressure. So that is actually what we are going to calculate going forward in this session and many of the coming sessions that will follow. I believe this is clear to you. I mean, this should at least be the motivation for going forward, so as to why are we so much interested in solving the Navier-Stokes equation. All right, so with this motivation in place, let's now look into solving certain very simple cases of calculating the velocity profile using the Navier-Stokes equation. And one such case, I believe we have done a very similar example in the lecture series. But so this example that we will solve is kind of a so this example that we solve is a kind of an what you say an extension of the problem that you solved in the lecture series. So I believe you have in the lecture series we have solved two different kinds of problem. One is a Couette flow, where you have a plate and the and the upper plate was moving with some velocity u naught. And then you also solved a different problem where the both the plates were stationary and the fluid was actuated by applying a pressure gradient. Now in this problem, what I did is I superimposed these two problems and I said that now calculate the velocity field for a fluid, okay, which is actuated by a constant pressure gradient, which is given to you, and also the upper plate which confines the fluid with the lower plate involved. So this upper plate also move in the right hand side direction along the x-axis with some given velocity u naught. Okay, so this is something that you are given. So I hope you can realize that this is just a superposition of the simple Couette flow plus the plane parabolic flow or the plane Poiseuille flow. Okay, where if you dissect this problem, you'll basically get these two problems, which you did in the lecture series. Okay, so this is the given problem, and again the objective is, as I said, which is similar to the one that we discussed here. This is basically a broad overview, but the objective is similar. We require to get the velocity profile, and after getting the velocity profile, our objective is to calculate the volume flow rate. Okay, so this is something that that we need to calculate when we solve this problem. I'll stop here maybe for a couple of minutes. You can go ahead and look into ways of solving this problem. As I said, the objective or the idea is now clear. We need to use the Navier-Stokes equation given this physical paradigm and then solve for the velocity field that are possible in this scenario. Okay. So we have a couple of more things. The channel width is given to be equal to h, and the fluid properties are as follows. Its density is rho, and its dynamic viscosity is given as mu. So this is what we get from the fluid properties. So okay, so since this is the first problem where I'm actually solving the full Navier-Stokes, I mean full means we'll look into analytical ways of solving the Navier-Stokes equation. But since this is the first time I'm doing, I'll write all the steps that are involved in this problem. But later on, when I solve similar kinds of problem, I'll skip certain steps because I believe that you are well aware of how these steps, the entire steps of the problem would look like. But however, that being said, I encourage that whenever you are solving this for an exam, or like basically for a subjective type exam, you should follow the entire steps of the procedure. For instance, starting from the assumptions, the governing equations, and then invoking the assumptions in the governing equation to get the simplified governing equation, and then the strategy to solve the simplified governing equation, and then finally incorporating the boundary conditions to get the unknowns uh, from from the integrations that we do. Okay, so this is the chronology that you should follow when you are solving these kind of problems, and the problems that will follow after this exercise. Okay, but for the purpose of demonstration, I will, since this is the first example that I'll show all the steps. But from the next example onwards, I'll skip I will skip certain steps, and I believe that you will fill those steps where when you solve that problem on your own. Okay. All right. So let's get started. So I understand we need to calculate the velocity profile, and you guys are excited to use the Navier-Stokes equation. But let's start from the very basic steps, which is actually writing the assumptions in this problem. Okay, so we'll start off from the assumptions. So what do we have here? So first and foremost, you can see. So first and foremost, you can see that the given flow field, the flow field is not given, of course, that is something that we'll calculate, but at least we know that there is a constant pressure gradient that is applied in a flow, and we are assuming that the length of these channels are infinitely long in the x direction. That is, these channels are going to plus infinity and minus infinity. Okay, this is something that we are assuming, which means that first of all, this is a steady problem that I'm solving for. Okay, so this is a steady flow that I'm considering. Okay, the second thing is that since the plate is infinitely long in the plus x and the minus x direction, okay, we sell so we are basically not interested in the beginning and the end effects. And the more technical way of saying that is that I'm considering that segment of the pipe where the flow is fully developed. Okay, so I'm considering fully developed flow. Again, I say the consequence of assuming that the flow is fully developed is the fact that the velocity profile that I calculate here and the velocity profile that I calculate here, that will just be the same, and it will not be a function of x, because I'm saying that the only way it can be a function of x in this given scenario is when I looked into the beginning and the end effects. But I'm saying that I'm neglecting the beginning and the end effects. So in other words, I am not interested in looking what is happening at the start of the pipe and what is happening at the end of the pipe. Rather I'm looking into a section where the effects of the flow is such that it is not changing along x, basically. Okay, this is the consequence of assuming that your flow is fully developed in nature. Okay. All right, and the third assumption is that is straightforward, because we are using the fact that your divergence of velocity field is 0, which means that we are considering an incompressible flow. We are considering an incompressible flow. And also, we'll consider here that there is no body forces inside the fluid. Okay, so no body forces. And fifth, this is kind of like so the fifth assumption, which will assume that the flow is unidirectional. This is anyway in accordance with the fully developed nature of the flow, and we'll assume that the flow is unidirectional in nature. Okay, or maybe I'll write that unidirectional flow. Okay? So this is an unidirectional flow. Okay. All right. So these are the assumptions. I believe the assumptions are cleared. Okay. These are the main assumptions. There can be some other assumptions as well, but these are at least the main assumptions that you should write and should consider when you are using the Navier-Stokes equation. Okay. So then if we are done with the assumptions, and I believe I believe this you are with me on this so far, then let's write the governing equations. So the governing equations. Okay. All right. So as I said, we are just now going to encounter two equations. One, the continuity, and second, the Navier-Stokes equation. Okay. So let's start from the simple one, or the simpler one, I would say, that is the continuity equation. Okay. So we all know that when we use the assumption that the flow is incompressible, the continuity equation just boils down to divergence of velocity is equal to 0, where this v is the unknown velocity profile that we are going to solve for, is equal to uex plus vey plus wez, where at least now you know that these u, v, and w are the x, y, and z components of the velocity field, and this ex, ui, ez are nothing but the unit vectors in the x, y, and z direction. That's it. This is something that we have already seen in the last week's class. Okay, and then this delta dot is what we call as the divergence operator. So this is the divergence operator, and this is of the form del del x ex plus del del y ey plus del del z ez. So typically, if you operate this on this vector field given by v, you will just end up, so what you do need to do, you just need to take a dot product between this and this. And you know that taking a dot product between this and this will give you, so you will have a non-zero component, which will look like del u del x, plus you will have del v del y plus del w del z to be equal to 0. It's just a simple dot product between this and this. That's it. That's all that we are doing. Okay. So you cannot have terms like del u del y typically, because when you do this ex dot ey, this will typically go out to be 0, because you know that your x and y, ex and ey are two orthogonal unit vectors. Okay, which means that their dot products between the two are going to be just equal to 0. Okay, I hope this is clear to you. Why we get this form, why and how we get this from this form. Okay, so that's it. That's the continuity equation that we have. But remember, we have to now use the second assumption, which is that it is just a unidirectional flow. That is, we just have a flow that have a velocity field in just one direction, and in this case, it is just the x direction. This is the consequence of the physical paradigm that we are given. Okay, which then means that I will not have a y component of velocity, I will not have a z component of velocity. Okay, so this is a consequence of assuming that the flow is unidirectional. Okay, I hope you understood. So remember, this is a consequence of using the fact that your flow is incompressible, and then invoking these two terms to 0 is a consequence of assuming that the flow is incompressible plus the flow is unidirectional in nature. Okay, so then we have just this term, which is del u del x equal to 0. So then what does it say? Can you tell me what del u del x equal to 0 implies from the continuity equation? So it just says, so this del u del x equal to 0 just says that the velocity field, the only velocity field that we have, which is the x directional velocity field, this x directional velocity field is not a function of x. Okay, this says that your u is not a function of x, which then means, and I hope you can realize that in this problem, since it's a 2D problem that we are looking at, that means I'm not interested in this z direction, because I'm assuming that the plate goes to, so the width of the plate is long enough such that whatever happens in this, so whatever happens basically in this section will also be happening at all other subsequent sections along it with, which is a kind of saying that your variables are independent of the z direction typically. Okay, so then what we can say is that since your u, which is the x directional velocity, is not a function of x, and I know that my variables are not going to be function of z as well, that means that your u, which is the x directional velocity, this is a function of y only. Okay, which means that the velocity field, which is the x directional velocity field, which is non-zero in this case, is just going to be a function of y. This is what precisely the continuity equation states when we invoke the assumptions in the continuity equation. Please let me know if you have any doubts until this point in solving this example. I understand this is a very simple case, but I'm deliberately going very slow since this is the first example that I'm showing for the case of a rectilinear unidirectional flow. But I'm also trying to say what are the few nuances that you need to understand when you actually invoke assumptions into the governing equation. Okay. All right. Any questions until this point? So if I write it down, I must say that my so this statement is that the x directional velocity, which is u, is a function of y only. Okay, that is the consequence, again I say, of invoking the assumptions into the continuity equation is what we get here. Okay, any questions until this point? All right, I believe there are no questions. Okay, then what's next? What are we going to do next? See, this u of y is still an unknown, right? We just have, so we just got certain, directions now into solving the velocity profile. The fact is that we at least now know that we just need to solve for just one component of the velocity profile, which is just the x component, and we know that its variation is just going to be in the y direction. Okay, that is something that we know at least, but still we don't know what this velocity profile looks like, right? And for that, what we need to do is we need to use the Navier-Stokes equation. That's all that we need to do, okay? And can you tell me which component of the Navier-Stokes equation should we use in order to determine u? Because I told you, right, that Navier-Stokes equation is a vector equation. So basically, if we expand that vector v, we'll get uex plus vey plus wez. But we know that we just have a non-zero x component, right? Which means it just suffices to consider just the x momentum equation in order to evaluate the velocity profile. Because we know that the velocity profile is just going to have one component, one non-zero component, which is the x directional velocity. Okay. So what we'll do is we'll just write the second governing equation, which is the x component of the Navier-Stokes equation. So I'll just write down the entire x component, and then we'll invoke the simplification just the similar way we did with the continuity equation. So the x component equation will look something like this. So it is rho times del u del t plus u del u del x plus v del u del y plus w del u del z, but we'll not consider the w term. But anyway, let's write it for the time being. So it's going to be w del u del z, and then this is going to be minus of del p by del x plus what, mu times del square u by del x squared plus del square u by del y squared plus del square u by del z squared, okay, plus rho times the body force in the x direction. Okay, this is the complete Navier-Stokes equation when we write. So basically what we are doing is we are just writing, I believe you can understand that we are just writing this equation in the x direction. That's all that we are doing. Okay. The first term is this, which is rho times the material derivative of dv dt. This is the second term, which is just del p del x. This term, this is the Laplacian of the velocity field. This basically boils down to this term when you write the Laplacian for just the x component, which is this, and then we have the body force, which is rho times bx. Okay. I hope you can understand the different terms that are there in this equation. And please let me know if there are any doubts that are there which you seek to clarify. Okay. All right. So then let's invoke the assumptions now. So we know that the first assumption is that the flow is steady, which means that this term will just go to oblivion. I know that I just have a rectilinear flow, which means that the y and z component of the velocity will just go to 0. These two terms are 0. Okay. I know that from the continuity equation that del u del x is 0, which means that u is not a function of x, which then means that this term will go to 0, this term will go to 0, this term will also go to 0. Okay. And I said that there is no body force, there is no active body force inside the fluid's control volume or inside, or basically inside the two plates. Okay. Which means that this rho times bx will also go to 0. So what we get after invoking all the assumptions is that the left hand side is 0, the right hand side is minus del v by del x plus mu times del square u by del y square. That's it. Okay. But I hope you can realize that in the continuity equation, we just say that my u is just a function of y only, which then means that this partial derivative, that is del to u by del y square, this will simply just be an ordinary derivative now, because we know that I just have one independent variable on which u depends on. So this is just going to be d2u by dy2. Okay. Which then means that my d2u by dy2 is going to be 1 upon mu times del p del x. Okay. That is something that you get. And this is the simplified form of the Navier-Stokes equation written in the x direction that you get when you invoke all the assumptions, again I say, that are pertinent to this physical example that we are considering of flow driven by a pressure gradient and a plate which is moving just in the x direction. Okay. Any questions up to this point? Okay. If no questions, then let's do one thing. Let's try and see what will be the Navier-Stokes equation in the y direction. Okay. Let's see what do we get when we just invoke all the assumptions in the Navier-Stokes equation in the y direction. Okay. Let's just see and try to, let's invoke the assumption and see what do we get there. Okay. So now if I write the y momentum equation, so can you guess what do we get when we invoke these assumptions in the y momentum equation? Okay, let's try and see. So let's write the y momentum equation just how we wrote for the x momentum equation. So the y momentum equation will just become rho times, now it will be del v del t, where v is the y component of the velocity, u del v del x plus v del v del y plus w del v del z. Okay. And then this is going to be minus of del p by del y plus mu times del square v by del x squared plus del squared v by del y squared plus del squared v by del z squared. Okay. Plus rho times by, which is the body force in the y direction. Now, if we apply all the assumptions, let's see what do we get. Okay. We have a steady state, which means this is 0. I don't have any y component of velocity because I know that this is just a uniform flow, which means that v is 0 throughout. Okay. Which means these terms are just 0. These terms will also be equal to 0, and I don't have a body force. Okay. Which just means that the consequence of that we get from the y momentum equation is that del p by del y is equal to 0, which says that my pressure is not varying along the y. So my pressure is, so this says that my p is not a function of y. Okay, this means that so maybe I'll name this as equation 2 or maybe 3 because 2 was the other one. Okay, so this means that now if we invoke this this information into equation 2, I can then rewrite equation 2 as, so rewrite 2 as, so what do we get? So we get d2 u by dy2 equal to 1 upon mu. Now instead of this being a partial derivative, now since I know that my p cannot be a function of y, it can at most be a function of x. So then this becomes dp dx. Okay, but we already know that in the physical problem, the flow is being actuated by a constant pressure gradient, which means that the only way this dp dx can be non-zero is equal to the applied pressure gradient, right, which is just equal to g in our scenario, which is given to us. I repeat, and this is important. Okay, see, I know that my pressure can't be a function of y, it can at most be a function of x, but I already know from the problem that in order to actuate the fluid, in addition to this plate, what I am doing is I am actually applying a pressure gradient which is constant throughout this x direction, and this is given to us, which is g, which means that the only possible way it can manifest in this problem is that dp dx has to be equal to g. Okay, which means that this dp dx is just a constant and is equal to g. Okay, you can think of it, you can think of this like what in a mathematical perspective as well. See, the term on this, on the left hand side, this is d2u by dy2. So this has to be a function of y. Okay, and the term on this, you are saying that a function of y is equal to something which involve x. So this equality will only hold good if, number one, this dp dx is 0, that is one case, or this dp dx at most have to be a constant. It cannot be a function of x if you want to write down this equality, because in no way you can say that a function of y is equal to a function of x. I hope this is clear. So the only possible solution in this case is that, since we know that dp dx cannot be equal to 0, because we know that there is an applied pressure gradient, the only possible solution is that dp dx has then to be equal to a constant, because we know that there is a constant pressure gradient that is applied throughout the channel in order to actuate the fluid, which then means that I can now write dp dx is equal to just g, and this g is given to us, this is the applied pressure gradient. Okay, so then I can write this as d2u by dy2 is equal to g, and in fact this is going to be g by mu, because there is already a mu involved, where mu, you know, right, this is just the dynamic viscosity of the fluid. Okay, and then that's it. Now what we need to do is we just simply need to integrate. So I hope you can realize that this is a second order non-homogeneous ODE. Okay, but this is integrable. So what we'll do is we'll integrate this once. So integrate with respect to y. Okay, so let's see what we get. So what we'll get is we'll get du dy if we integrate it once with respect to y, and this would be gu integral dy is just going to be equal to y plus a constant c1. Okay. I hope this is clear to you. And then what we'll do is we'll integrate it once more in order to get the velocity profile. So integrate again with respect to y, and then what we'll get is u as a function of y is going to be g by 2 mu y square plus c1y plus c2. Okay, so that's it. So that's the velocity profile. That's what we had been looking for, right? where you can see that this C1 and C2, these are constants of integration, and typically we are supposed to get two constants of integration just because this is a second order ODE that we are solving for. Okay, so since it is second order, we are bound to get two constants of integration. Okay, all right, that's it. Then the job that we are left now is just to calculate these constants of integration C1 and C2. For that, we'll use the boundary condition that are given to us. So let's try to work out the boundary condition now. So that we'll see from the physics of the problem. So we can see, so what can we see? We can see that the lower plate is stationary, okay? Meaning that this plate is fixed. So from the no slip boundary condition, you can say that at y equal to 0, my u has to be equal to 0. Typically because this plate is stationary. That is a consequence of the no slip boundary condition. And at y equal to capital H, I know that the top plate is actuated in the right hand in the right direction by a magnitude u naught, which means again due to the no slip condition, it just says that since the plate is moving at u naught, the next layer of fluid which is attached to the plate should also move with u naught, typically because of the no slip boundary condition. Okay, so that means that u at y equal to h is going to be equal to u naught. Okay, and these are, as I said, these are what we get from the no slip boundary condition. Okay, and that's it. We just require two conditions to evaluate the two unknowns C1 and C2, right? So let's then apply this. So what we have is, we know that at y equal to 0, my u at y equal to 0 is equal to 0, and this is because of the fact that my lower plate is stationary, and I'm using the no slip boundary condition as I just said. Okay, and then if we use this, what we'll get is we'll get 0 equal to C2. Okay, if we just use this in this equation, we'll just get C2 to be equal to 0. Okay, maybe I will name this as 4. Maybe I'll name this as 4a. Okay, so this is one constant that we got, that your C2 is just equal to 0. From the second boundary condition, we'll say that my y, so y at y equal to h, I know that my u at y equal to h is equal to the plate velocity, which is u naught. This is because the upper plate is moving towards positive x-axis with velocity u dot. Okay, and as a consequence of the no slip boundary condition, the fluid which is just below, the layer of fluid which is just below the upper plate will also move with the same velocity as that of the plate. Okay, that's why we are writing this boundary condition. So then if we, so let's use this here. So then what will we get? So we'll get u naught equal to, now y will become h. So this is g by 2 mu h squared plus C1h plus C2. Okay, and but I know that my C2 is already 0 from 4a, which then means that my C1h is going to be minus of g by 2 mu h squared, which then means that if I divide this by h, we'll get that my C1 is equal to minus g by 2 mu h. That's what your C1 is. Okay, maybe I'll call this as what, 4b. All right, then we are all set to write the full velocity profile, which is u as a function of y is what? So this is equal to g by 2 mu y square plus c1 y plus c2. I know c2 is 0 and I know c1 is basically equal to this, which means I can then write it as oh, I think I made a mistake. I'm sorry, I just made a mistake here. I'm very sorry. I just made a mistake in simplifying this. So C1, see there is a U naught. This U naught is there, right? So this C1 H is going to be U naught minus G by 2 mu H squared. Okay. This is C1 H. And then my C1 is going to be u naught by h minus g by 2 mu h. That is what going to be my C1. Okay. Apologies for the mistake. This is going to be my C1. Okay. All right. So then if we substitute this C1 and C2 into equation, or this is 4. If we substitute these C1 and C, so what we do is we'll just substitute the value of C1, we'll substitute the value of C2 in equation 4. Then what we will get is we will get u as a function of y is equal to g by 2 mu y square plus C1y. So my C1 is equal to u naught by h minus g by 2 mu h times y. This is C1, and C2 is anyway equal to 0. Okay. So if we simplify this a little bit, I'll show you something interesting. Okay. So this can be written as g by 2 mu y square plus u naught y by h minus g by 2 mu hy. Okay. And then what I will do is I'll maybe write it as u naught y by h plus g by 2 mu into y square minus hy. Okay. So then what do you see? Do you see some similarity with two problems where, in one problem there's a plate which is just moving with u naught without any imposed pressure gradient, and in the other problem there's an imposed pressure gradient but the plates are stationary. So I believe you can see that this problem is a linear superposition of these two problems. Okay, where in the first case you just have a plain quick flow, and in the second case you just have a plain parabolic flow. So one thing that you can see is that the velocity profile that we get here, that is u of y, this is equal to a u. So maybe I'll write it as so this is equal to a u due to quick flow. I'll write it as COUT, which is a function of y, plus u due to plain parabolic flow or plain possible flow, which is a function of y, where this u quick flow is just u naught y by h, and this u plane parabolic flow is g by 2 mu y square minus hy. So then what do you conclude? You conclude that you can, without doing the algebra and all this analysis, you can still find out the solution to this combined problem, which has a combination of a pressure gradient and a imposed plate velocity, as the combination of the two problems, where in one problem you have the flow that is generated just by a moving plate, and in the second problem you have a flow that is generated just by a pressure gradient, which the solutions of which you already know from that is basically what we have already solved in the lecture series. Okay, and this you can do, that is typically because of a very important principle that is known as the principle of linearity. And the principle of linearity states that if you have a governing equations, for instance, see, equation 2 is an ODE, but we know that this is linear. This is linear in U, right? So if you have linear equations, what you can do is the equation to a complex problem, that is the problem that you get by adding two problems, is equivalent to the solutions of the simpler problems, where you can superimpose the two solutions. Okay, and this is actually a consequence of linearity of the governing equations. So that's what you already saw, that your solution that you get when you have a flow that is being actuated by a plate which is moving with u naught and a pressure gradient which is constant and with magnitude g, is equal to the flow field that you generate when you have a quick flow, where you just have a plate that is moving in u naught, plus a problem or the flow that is generated when you just have a pressure gradient that is applied in the two direction without the motion of the flow, two plates, which are basically these two examples. And that's when when I said at the beginning that you can dissect this problem into two simpler problems because of the fact that your governing equations are linear in nature. Okay, but if you have a non-linear governing equations, you cannot apply this principle of linearity. Okay. All right. So this is something that that you need to understand. So I'll write it down that under special cases, if let's say u naught is 0, that is when the upper plate is stationary, your solution just becomes uy which is equal to g by 2 mu y square minus hy, and this is just equal to u of a plane parabolic flow that you derived. Okay. On the other case, if my g is equal to 0, that is when I don't have an active pressure gradient, I can say that my u is just equal to just this term, which is u naught y by h, and this is a linear velocity profile that you get when you just have a Couette flow basically. So this is a Couette flow. Okay, that is something that you, so sorry, this is g naught, g equal to 0 basically. Okay. All right, so I believe you have got, you got the gist of the consequence of linearity at least. Okay. So one final task that is remaining in this problem is that finding out the volume flow rate. Okay. So what you need to do is you now need to evaluate the volume flow rate. So for the volume flow rate, what you need to is, this is similar, and this we had been doing in the first example that we saw today, and we'll apply the same principle, because we know that my velocity profile is in principle varying along, you know, the so my velocity profile is varying along the y direction. This is x and this is y. So what I will do is I will pick a particular y, choose a small differential area there. So the differential area that is going to be there is going to be, so its height is going to be dy. So this is dy, and its width is going to be inside this plane. So this width is going to be this. This is width. Okay, where this width is taken to be equal to b. Okay, and then what we'll do is we'll calculate what is the differential volume flow rate that is coming out through this differential area. Okay, and think of it like this is, the plates are kind of going to infinity in this line, and think like your b is very much greater than 1. That's where this condition applies actually. Okay, this is the upper plate and this is kind of the lower plate. That's all that we are doing here. Okay, I hope you got this thing. So what we are actually trying to do it, we'll calculate what is the fluid that is basically coming out through this stripped portion. This will give you the differential volume flow rate, and then we'll integrate it from 0 to h, because this height is equal to h, to get the entire volume flow rate. So my differential volume flow rate, as I said, my differential volume flow rate which we'll call it as dq, is just the velocity field times the differential area, which is going to be b times dy. That's it. Okay. So if this is the differential volume flow rate, then the total volume flow rate, or the volume flow rate, that you will get is just integral from 0 to h, okay, u y v dy. Okay. And we know what is ui, right? We already evaluated the velocity profile, which is just this. So we just need to substitute this velocity profile. So what is the velocity profile? It is just integral 0 to h. You have u naught y by h plus g upon 2 mu y square minus y h. I think that's the velocity profile that we have. And you need to integrate it from 0 to h. I think that's what we have, right? Yeah, exactly. Okay, so that's it. Let's do the integration. It's a very straightforward trivial integration. So this is q. And remember, there is a width also here, but I'm assuming that I can consider that my width. So what I'll do is I'll bring the width here. So this will become volume flow rate per unit width of the plate. This is the volume flow rate per unit width. Oops. And then this is going to be integral from 0 to h u naught y by h plus g by 2 mu y square minus y h of dy. So let's do this integration. So this will be u naught by h times integral y dy is going to be y square by 2. Okay. Okay, so integral y dy is y square by 2. So then this becomes h squared by 2. Then I have g by 2 mu times y square dy is y cubed by 3. So this will become h cubed by 3 minus h times y dy is going to be y squared by 2. So this becomes y squared by 2. Okay. All right. So this integral done then becomes u naught times h by 2 plus g upon 2 mu times h cubed by 3 minus h cubed by 2, which will give you u naught h by 2 plus g upon 2 mu, okay, h cubed by 6. I think it will be minus of h cubed by 6 because h cubed by 3 minus h cubed by 2 will give you minus of h cubed by 6. Okay, that is going to be your volume flow rate, Q by volume flow rate per unit width of the pipe. Okay. All right, that's it. That's all that we are required to solve in this example. Okay, I will maybe stop here for a couple of minutes. You can let me know if you have any doubts. That's it. That's the volume flow rate per unit width. Okay. Okay. All right. I'll stop here for a couple of minutes. If you have any questions, queries, or comments, you can let me know. Or maybe if you are watching this video later on, then please feel free to use the discussion forum. There is a section known as Q&A written in the website. So it's there in the website where you can click and then you are redirected to the discussion forum where you can pose your questions if there are any queries at your end. Okay. All right. So what we'll do is we'll do one more quick problem. That's a very simple problem. And then we'll call it a day. And then we'll meet in the next week's live hour. But before that, I will just come in 2 minutes. Uh, I'll just have some water and come in 2 minutes. Okay, sorry for the interruption. All right, then let's do a quick problem. That is, you are given a fluid flow, okay, and then what you need to do is you just need to calculate the shear stress. That's all that you need to do. This problem is actually there. A similar problem is being asked in your assignment, and I think this is sufficient. So whatever discussions that we have, this is sufficient, for you, at least at your end, for you to actually solve the assignment. And of course, you also need to watch the lecture series as well. So the lecture series complemented with this discussion are sufficient for you to solve the assignment at your own without using any, external sources for as your help, basically. Okay, so what we need to do is we just need to calculate the shear stress here. So we know that this is a quick flow. So we all know that the governing equation is just going to be d2u by dy2. I'm not doing the steps as of now because, as I said, the last problem we solved it very detailed way. Now I'll skip those steps. But if you are doing this at your end, start from the assumptions, the full Navier-Stokes equation, invoke the assumptions, get the ultimate, get the simplified version of the governing equation, and then integrate them to basically get the constant, apply the boundary conditions to evaluate the constant. That's all that you require. Okay, so then if you kind of integrate this twice, what you'll get is you'll get a velocity profile as ui equal to some c1 times of y plus c2. This is what you get, because see, if you integrate this once, you'll get du dy equal to c1. If you integrate it twice, it will get u equal to c1 y plus c2. That's all that I have written here, basically. Okay. So now what you need to do is you just need to apply the boundary condition. So you can say that at y equal to 0. So my x is this and my y is this. You can say that your u is equal to 0 and at y equal to h, your u is equal to u naught. From which you can say that your if you use these two conditions, if you just use these two conditions in here, you can say that your u is just going to be u naught times y by h. That is exactly what we got when we solve the first part of this problem, where we evaluated this velocity field. That is the velocity field due to just the actuation of the right or actuation of the upper plate only. Okay. All right. So this is what your velocity profile is. Okay. I don't think I need to elaborate on this much because we had been seeing this repeatedly. Okay. So now the the calculation is to calculate the shear stress. Okay. So the shear stress, first of all, you need to understand that the shear stress, or sometimes it is called as the deviatoric stress, this is actually a tensor. Okay. And this is actually written as the dyadic of the velocity field plus the dyadic of the velocity field transpose. See, this is not a dot product, this is not a cross product, this is a dyadic product. Okay. And dyadic of a vector will always give you a tensor. Okay. So this is how your stress would look like. Okay. So if you use something, so there is something which is known as the Einstein's notation. We will see a glimpse of it maybe in the next to next class. There is something which is known as an index. So this is known as an index notation actually. Sometimes it is, I guess it is also called Einstein's notation. So in index notation, what you do is we represent variables using something known as I and j's. So since stress is a tensor, we represent this using two, independent variables known as I and j, and this typically comes out to be del uj by del xi plus del ui by del xj. So these I and j's, when they are written like this, these are known as free variables, or non-repeating variables. So two free variables indicates that it's a tensor. One free variable indicates that it's a vector. If it does not have any free variable, it's a scalar basically. Okay. So this is one way of writing stress in the index notation. We'll not go into the details of this now, at least. And this is one way of writing stress in the vector notation. But so typically now, since this stress is basically a tensor, you are supposed to have 9 components. This is something that we discussed in a 3D geometry. So for instance, you are going to have tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, and tau zz. Okay, these are the components of stress, or the deviatoric stress, or sometimes they are also called as the viscous stress. that you get when you write this in 3 dimension. But in the case of a plane, and of course, tau ij is basically equal to tau ji, which means that this is a symmetric tensor, meaning there's these two components are going to be equal. These two components are going to be equal, and these two components are also going to be equal. Okay, so then what you can show is that in the case of a in the case of a plane fluid flow, or in the case of unidirectional flow, you will only encounter tau xy or tau yx, which is going to be, this is precisely going to be mu times del u by del y plus del v by del x. Okay, but it's just a unidirectional flow, right? That means that this v is equal to 0, and then I just have tau xy, which is going to be mu times del u by del y. Okay, and I know what is u, right? U is this, so del u by del y is going to be u naught by h. Okay, so this is going to be mu times u naught by h. Okay, so this is what your stress field is going to be. Okay, this is what your tau xy uh, is going to be. So it is mu times u naught by h. This is typically what your stress field is going to be. So you can see that when you have a linearly varying velocity profile, your stress is constant throughout. That is, if you plot if you plot the velocity field here, your velocity field is very like what? So this is going to be your velocity field. This is linear, which is u naught y by h. This is the variation. But if you plot your stress field is just going to be this. It's just going to be a constant uh, with magnitude what? This is the magnitude, okay? Mu u naught by h. Okay, this is your velocity field. So this is your stress field, and this is your velocity field. Okay, I hope this is clear to you. Okay, so that's typically, so you can see that your stress is constant, and sometimes there's also one more thing which is known as a wall shear stress, which is actually your tau evaluated at the walls basically, which in this case is tau at y equal to 0 and h, and you can see that this is anyway going to be equal to your mu times u naught by h, because you know that your stress is constant throughout basically. So your wall stresses is equal to the bulk shear stress which is at the fluid basically. Okay, that's also one of the important conclusion here. But for example, let's say you have a velocity profile in the second scenario, which is like the plane possible profile. For instance, you have the velocity profile like g by 2 mu uh, y square minus yh. Okay, then if you calculate the stress, you just need to calculate du by dy. Okay, that's all that you need to calculate. So then this becomes g by 2 mu twice y minus h. And then if you choose your, so remember we use the coordinates like here. So your x is here and your y is here. So your stress then becomes, first of all, your stress becomes mu times du by dy. So then it becomes of g by 2 times 2y minus h. Okay. Then your wall shear stress is at y equal to 0 and at y equal to h. So if you calculate your wall shear stress, your tau walls at y equal to 0, it becomes what? So hold on. Becomes, let me first check the axis. So okay. So it becomes, so at y equal to this is just, so your tau is just minus of gh by 2, and at your wall shear stress at y equal to h is going to be gh by 2. Okay, and then you can see that is it correct? At y equal to h. Okay, yeah. Okay, then you can see that at the mid plane, that is at y equal to h by 2, you can see that your tau is equal to what? So your tau basically comes out to be equal to 0. Okay, which means that your shear stress profile in this case varies something like this. It's going, so it is positive here, it is negative here. So it is basically varying something like this. Okay, so this is so at the upper plate you have GH by 2, the lower plate you have minus GH by 2, and at the mid plane, that is at y equal to h by 2, you have your shear stress to be equal to 0. See, that is obvious, right? Because the shear stress is actually the rate of change of u with respect to y. And you know that if you draw the velocity profile, this velocity profile is going to come out as what? So this velocity profile is parabolic in nature, right? So if you draw the velocity profile, so you see that it have, see, this is very interesting. You have a positive slope here and you have a negative slope here. Okay, which means that that's the reason why your shear stress is positive here and that's the shear stress is negative here, because tau is always proportional to du by dy. It is the rate of change of u with respect to y. It's kind of like the slope of this curve that you are actually evaluating. And that's the reason why, you have a negative shear slope, negative shear stress when, you kind of like come below this curve at y equal to h by 2 typically. Okay, that's the idea. So this is the velocity profile. This is basically the velocity profile. And this is your shear stress profile. This is your shear stress profile. Okay. All right. So that's for, that's for, this is, remember, this is for the case when you have a plane parabolic flow or a plane Poiseuille flow. And this is for the case when you have a Couette flow. Okay. That is this scenario, basically. All right, so that's it then. We looked into certain interesting things today. I hope you have enjoyed this. In the next week discussion, we'll move into unidirectional flows in curvilinear coordinates. For example, Hagen-Poiseuille flow is something that we will see, and there is something known as a Taylor-Couette flow. We'll also look into this Taylor-Couette flow. Typically, this is the flow that you get in the annulus between two concentric rotating cylinder. And we will see the interesting things of Taylor-Couette flows. Okay. All right. So that's it that we'll do today. Thank you for attending these sessions. If there are any questions, as I say, please feel free to post it in the discussion session of the course, and we will be there to answer your queries. And if you wish to attend the live session, you can join the link and feel free to address your queries there. Okay. All right, then thank you very much. We'll meet at the next week, in the next week.